And while we want to address all the different ways of learning, this means that usually in college we drop this manipulatives, which is in earlier years it's really a popular way to do, and it helps a lot of students. So activities are going to bring this back somehow. Maybe they are a little bit different level than you will expect in high school or elementary school, but because we'll use some graphing and stuff like this, but that would be sort of experiential learning. Now, this link gives you the survey that students actually can check what kind of learners they are. And this, you answer like few questions, and you start understanding what kind of learner you are. And I do recommend that you give it to students. They, at this age, they really like to learn about themselves. And what I want to say that all these activities, they address also students with different abilities to focus. So, you know, the tricks, they get student attention, they promote discussion, lecturing, conjecturing, and so on. They teach algebraic skills, and they bring fun to algebra classroom. And they also get students to ask questions. So they, at some point, they really start to feel that there is nothing like a stupid question, which is good. Now, what I want to start is with something that many of you may know, and usually what I do, I actually have a huge box of dice and I give them to students and we start playing with it. But instead of doing it this way, I will stop for a moment sharing my screen. Okay, and so you will see the camera, right? And you will see my dice. So what's the first thing? I have two dice, and I'm not looking at them. As you see, I actually cannot see them, but I stack them as a tower. Okay, and some of you may know this trick, of course, but if I look around the tower, I can see a lot of numbers, but my question is, what is the sum of the sides that I don't see? Anybody has an idea? Open your mic and say, what's the sum of the sides that I don't see? So what I don't see the one at the bottom. And I don't see this two that top and the bottom are glued together. Anybody?
6.
What do you think? 6? Anybody else?
13.
13. So let's check. Okay. I'm keeping this out. What do you have? In here, you have 6 and 4, that's 10. And at the bottom, I have 3, so it's 13. Okay, let's see, maybe this was a lucky guess. Okay, how about now? What do you think? What's the sum of the ones that I don't see and you don't see? I mean, you don't see a lot because you don't see the sides, but you know, if you would have it in your hands, you would see it.
10.
10. And okay, how do you, well, I'm not going to tell you how I'm doing it, but now what I will do, 10 is right, and I was able to guess. Now I will take 3 dice and I will stack them. Okay, and I'm asking the same question. Okay, what's the sum of the sides that cannot be seen if I walk around?
18.
18, right? So you're getting it. And then what can I do? I can, of course, put one more, right? And ask the same question. Okay, so perfect. Here we are. We go back to our, I just wanted to make it as an exercise, okay? And all these things will get together. So we can guess, okay? And what's the reason that we can guess? It's because we can, we know how the die is built. So every die has sides built in such a way that the opposite sides add up to 7. So 6 and 1, 7. 4 and 3, 7. 5 and 2, 7. So because of this, if I have a tower of 2, then everything that's parallel to the ground has to add up to 14. I'm seeing 5, so I subtract 5 on this one, right? I'm seeing 1, so I subtract from 14 1. If I have 3 dice, then the sum is 21, right? If I have 4 dice, then the sum is 28. So I subtract what's at the top. Okay, and okay, we had fun. So where is the algebra? Well, then you ask the students to guess what will happen when you have 5. And then, of course, they will say, okay, 35 minus x, x is what's at the top, right? And then you say, okay, what if I keep stacking this dice, right? I can put one more. What if I have n dice? What would be the sum of the ones that I don't see? And they come up with the formula, or you help them to come up with the formula, 7n minus x. So we got their first formula, and now you can play with this. How about if I put my tower down? So now I don't see more things, right? I don't see what's at the bottom. I don't see anything that it's connecting here. So in here, I have 1, 2, 3, 4, 5. So this way, right, I shouldn't see, I would have the total, if I count all these parallel sides, the total would be 13, but let's say this one has 3, so I subtract it. This one is 5, so I subtract it. And then I don't see the opposite to this, 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 and so on. So if I calculate this one, oh, this is something wrong. But anyway, you can now stack tower upon the tower upon the tower, right? You can build them up. You can build castles, and you can ask students to develop their own formulas for whatever design they made. So that's an easy exercise, and many of you knew it. Now I will go to the next one, which you may know as well, because it's kind of popular. So I will magically make you do certain calculations, and whatever you come up with, I will be able to guess. Okay, so I want everybody to pick any number. Okay, pick any number. Now add 6 to it. Multiply it by 2. Subtract 10. Divide by 2. Subtract your original number. Okay, everybody ready? Add 6. Okay, and I will going to guess the numbers. Don't tell me. I'm thinking, I'm a magician, da, da, da. And your number is 7. Everybody got 7? If you didn't, it means you messed up in your calculations. So you see, I mean, magically, I made you think of a number that I wanted you to think of, which was number 7, which for many people is a lucky number, right? But that's the easy one. How about we do another guess my number? So pick any number. Okay, you'll have to do calculations, so keep your pencil ready. Okay, multiply by 4, add 10, double what you have. Okay, subtract 12, divide by 4, and tell me what you got. So any volunteers?
36?
36, so your original number was 17.
Yes.
Very good. Anybody else?
6.
6? So your original number was 2.
26.
Oh, 26, sorry. So your original number was 12.
Yes.
Yeah.
Correct.
Anybody else you want to try?
22.
22, so your original number was 10.
10.
10, your original number was 4.
That's right.
202.
Oh my God. So your original number was 50.
Can I say something?
Sure.
I played this trick, but what I've done is that when I multiply by numbers, I did not divide by the same numbers, and yet I can still guess. correctly.
That's possible. But you see, the thing is, what we're trying to do here. I mean, there could be a lot of different ways of doing this trick.
Mhm.
And I will explain to you how this one is done,
Yeah.
right? But the thing is, it's very catchy for catching attention to if you talk to the students, because they really think that you are a magician for a while, and they start to understand that you're using algebra, right? So how does the first one work? Remember, everybody got 7. So you picked a number. I didn't know what you picked, right? So I call it X. Then you added 6. Then I said multiply by 2. So you have to multiply the whole expression by 2. So I'm getting 2x plus 12,
Yeah.
right? Subtract 10. So I have 2x plus 2. Divide by 2, you're getting x plus 1. And I take away your original number. So x is gone, I'm getting a 1. This would be okay to stop here, but I don't want to have it that obvious. So I'm saying add 6 and you're getting a 7. See, and from all these calculations, no matter what you start with, you end up with 7, right? So that's an easy trick, and so on. And you say your number is 7. Now, how about the other one? Well, the other one, I also said pick a number. So it was x, right? Multiplied by 4, add 10, right? Double. So you got 8x plus 20. Take away 12, and I want to take away 12 because I want this divisible by something, right? Divide by 4, you got 2x plus 2. Okay, and this is, whoever was telling me your number was equal to 2x plus 2. So when you gave me a number, let's say it was 26, what I was doing very quickly in my mind, I was subtracting 2 and dividing by 2, right? Because this is equal to 26, so I need to take 2 away from both sides and then divide by 2 to figure out what x is. So, you know, my warning is you can pick up any formula that you want, right, to do your trick. For example, you can practice doing squares, right? Pick any number, add 1, square the results, subtract your original number, subtract your original number again. Well, so how does that work? What does it do? You pick a number, it's x, right? You add 1, so you have x plus 1, then you square it, so you have x squared plus 2x plus 1. Then I don't want to have this x here, so I take you to subtract it, and I tell you to subtract it away again. So if you give me, say, your answer is number 10, then if this is equal to 10, this is what you're telling me, I subtract 1 and take a root. See what I'm saying? So you can make up your own guessing things, but remember, at the end, you want to have a simple formula so you can remember how to quickly figure out what number was, you know, originally there, so you can figure it out. Now, how about we try to do a trick with two-digit number? Okay, so pick any 2-digit number. Look, positive natural number. Okay, I mean, no pi's, no e's, and so on. I want a 2-digit number. Okay, pick any 2-digit number. Okay. Now switch the digits. Okay, so you'll have two digits numbers. So say if you have 27, you have 72, or something like this. Okay, switch these two numbers. Okay, add both of these numbers together. Okay. And then what you get should be divisible by 11. So divide it by 11, and you're doing it for my benefit, so I don't have to do it. And keep this number. Okay. Okay, keep this number, and because I will be asking you about this number. Now, look at these two numbers that you had at the beginning. Okay, one of them is larger. So take away smaller from the larger. Okay, and this should be divisible by 9. So divide it by 9 and keep the result. So now I will ask you for two numbers. I will ask you for what did you get here and what did you get here? Okay, so what are, I want people to give me two numbers.
9 and 1.
9 and 1.
Yes.
So you have 9 and 1, so you have 54 and 45.
Yes, correct.
Anybody else?
7 and 3.
7 and 3. Okay, I got 7 and 3. So you have 5 and 2. 52 and 25.
Yes, correct.
13 and 1.
Say it again.
13, 1, 3, and 1.
13 and 1. So one of your numbers is 7, and the other number is 76.
4 and 0.
4 and 0. Oh, tricky. So your number is 2 and 2. So you pick 22.
Yes.
6 and 2.
6 and 2. Okay, 6 and 2. So your number is 4 and 3. 43 and 34.
3 negative 1.
No, it wasn't, but that's okay.
It wasn't. Say it again. 4 and 3.
No, my two numbers were 6 and 2 that I wound up with.
So 6 and 2, you're getting 4 and 2.
Yes,
Sorry.
it was
4 and 2.
24.
So 42 and 24.
Yes,
right?
yes, that's right.
Very good. Okay, sorry.
3
I-
negative 1.
say it again.
3 negative 1.
Well, no, I ask you to subtract bigger from the smaller.
Oh,
I mean, smaller from the bigger. Take bigger one and subtract
I
smaller.
did opposite. It's okay.
I mean, I can do it, but that, you know, I'll have to think a second.
It's okay.
Okay. Okay, so anybody understands how to do it? See, I'm doing it very quickly, so it must be easy.
It is x plus y divided by 2, x minus y divided by 2.
Well, yeah, but where is this coming from? So you see, I mean, I'm saying pick any two-digit number. So what am I using here is your position, right? So
Yes.
if number
10x
is
plus y. Yeah.
right, so it's 10a plus b. This is your two-digit number. Then I switch the digits.
Yes.
So it's 10b plus a. Now, when you add both of them, right, you will get 11a plus 11b. And I'm telling you to divide it by 11 because I don't want to do it in my mind, right? So I want you to give me the simpler answer. So what I'm getting in this position, what you're reporting to me is a plus b. Now, then I'm saying subtract bigger from the smaller. So you will get this one minus this one. So it would be 9a minus 9b, right?
Which is
And
divisible by.
exactly. I divided by 9, so I'm getting a difference of your two numbers. And now you say, okay, I got, say, 7 and 3. What do? I add these two numbers. If I add these two numbers, then b cancels, and I'm getting double a, right? So
That's the sum. Yes.
it's a sum. So I'm getting 2a, and what you give me these two numbers, I add them and divide them by 2. So I'm getting one of the numbers. And then I'm subtracting one from the other. Okay, because if I subtract a plus b, I take a plus b and I subtract a minus a plus b, right, from this one, then I get two b's. So whatever you're reporting to me, I'm first adding it and dividing it by 2, right? And I subtracting and I divide it by 2, that gives me the other number. Everybody with me? So that's a lot of fun as well, you know, if you try it in class. Now we'll try something a little bit different. And, you know, all these things that I'm showing you, they will add up to something at the end. So let's say that you have 4 stamps. And this stamps are, I mean, this is all days because this stamp is 1 cent, this stamp is 2 cents, this stamp is 4 cents, this stamp is 8 cents. So the first question is, okay, I want to mail a letter that you have to pay 11 cents for. So how do I pay for it? I need this stamp, I don't need this one, I need this one, right? And I need this one. Everybody with me? Because this one is 8 plus 2, that's 10, plus 1 is 11. Okay, so I'm checking if I can do it in various situations. If I need to pay 3 cents, then what? I take this stamp and I take this stamp, right? If I have to pay 6, then what I do?
4 and 2.
Yeah, 4 and 2, right? Okay, if I do, if I need 10, right? So I do it, you know, I mean, you can play this game in class, right? So you're getting 8, nothing, 2 and nothing. So it's sort of the way how to code certain things, right? If I want 12, see, I don't even put the stamps anymore. Yes, 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 no, no, right? Okay, and 9 is what? No, yes, yes, no, no, yes. Okay, so after we did this practice, I want somebody to volunteer. I need a volunteer. Okay, I want you to think of a number between 1 and 63. Okay, anybody?
39.
Okay, no, 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 don't tell me.
Oh, okay.
It's a magic trick. Don't tell me. Think of a number.
Okay.
Okay, but you know, you can, for example, write it in a chat to others. I'm not seeing the chat, so that's fine. Okay, so think of the number, and then I want you to tell me if this number is on this card.
Which card?
The first one.
Oh,
This card. Is it here?
Yes.
Yes. Okay. Is this number on this card?
No.
No. Is this number on this card?
No.
No. Is this number on this card?
No.
No. Is this number on this card?
Yes.
Yes. Okay. Is this number on this card?
No.
No. So you have thought of number 17.
Yes, correct.
Okay. Anybody else wants to do it?
40?
Don't
No,
say
don't
no.
tell me.
Sorry,
Don't
sorry,
tell me.
sorry.
Think of it. I will tell you.
Okay, I'll take a new number. My bad.
Okay. So ready?
Yeah,
Is your card on the? Is your number on this card?
no.
Is your number on this card?
Which the second?
This one.
Oh,
Second.
yeah, no.
No. Is your number on this card?
Yes.
You don't see my my pointer? No.
Yeah, I do. Yeah, I do.
So wait, on this one, no,
On the third one, the one that you're just pointing at is there.
it's there. Okay.
Yes.
What about this one?
Is it on the, yes,
Yes. Okay. Is it on this card?
yes, it is.
Yes, it is. Okay. What about this one?
Yes.
Yes.
Mhm.
Okay. So your number is 56, 60.
Yes. Wow. That's
Wow.
awesome.
Okay.
Thank
Anybody
you.
wants to try, or are we going to explanation?
That was fun.
Explanation.
Explanation. So, well, okay. Anybody wants to explain?
Hmm.
It is, I can explain.
Go ahead.
It is the it's binary in the upper corner.
Well, so in a sense, it is, well, yes,
Based-
it is binary in a sense, right? So see, if I look at the first card, then if I look at the binary expression, and now look, so this is sort of similar to what we did with the stamps. And I was saying, okay, if I have my number, whatever number I have, let's say that let's pick a number, say I have number, 21. Okay, so if I want to make 21, I will need a 1. I will need a stamp 1, so it's on my list, right? And then this is sort of going towards what we did with the stamps. If I need this, if I have a number in my head, I'm checking only the first number. So see in here, do I need a 1 to make this number? Do I need a 2 to make this number? Do I need a 4 to make this number? Do I need 8 to make this number? Do I need 16 to make this number? Do I need 32 to make this number? So for example, if my number is 53, let's say I have it here, then I'm checking, okay, I will need the stamp of 1, 53. I will need, and so as a magician, what do? If you say yes, I write down 1, okay? I keep 1 in my mind. If you say on 53, see, it's not on this card, so I'm not using 2. 53 is on this card, so I have so far 1 plus 4, right? It was here and it was here, so I have 1 plus 4. Now, is 53 in here? Right, it's not, so I don't need that stamp. Right, now 16, it's here, so I have 1 plus 4 plus 16 so far, because I'm taking this number. And then I'm looking at this one. Do I have 53 on this one? Yes, I do, so I need 32. So if I add 1, 4, 16, and 32, right? So 16 and 4 is 20. And 32 is 52, and 1 is 53. So I'm getting this number. So you understand what I'm doing? I mean, every time you say that the card is on your number is on the card, I'm adding the first digit on this card, the first number. And this is really writing in as a binary expression of the number. Okay, so we practice all of this and we'll see what does it have to do with algebra altogether, because we are supposed to be in algebra. Okay, so if I'm looking at the line, okay, how many points do I need on the grid to specifically say this is specific line?
At least 2.
At least 2, exactly 2, right?
Exact, yeah.
Yeah, if I give 1, that's not enough, because then if I give 1, I have a lot of lines. Say I give you 2, 7, then I have a lot. So if I give you 2 points, say this 2, then you can look at the equation and you can solve it and figure out which exactly line it is. It's y equals to 2x plus 3 in this case. Everybody agrees I need 2 points. Okay, so now I want you to write your own line. So pick any A, pick any B that you want. But since I will have to calculate a lot of in my mind, I would like you to have this A and B positive and smaller than equal to 10. Okay, don't take any bigger than that. So say line 7x plus 3, fine. 2x plus 15. I want you to write your own line down. Okay. Ready? Now, I want you to tell me how much is y when your x is 11?
23.
22?
23.
Oh, 23. Sorry, sometimes I cannot hear you. So I will tell you what is your line. Okay, your line is 2x plus 1.
Yes, correct.
Anybody else?
51.
51?
Yes.
51.
Mhm.
So your line is 4x plus what is it? 4, 6, 7. 4x plus 7.
That's right.
That's right.
Yes.
One more. Anybody?
66.
You got 66?
Yes.
Ah, so you got it tricky, right? Because it is what? Just 6x plus 0. Right?
Okay.
So your B is 0. Okay, I'm not explaining this one yet because I can tell you that I can do the same trick for parabola. Okay, so I mean, what kind of a trick is this? You're giving me 1 point and I'm telling you what line you have, right? That's against what we just said. We just said that you have to have 2, and I did it after 1. And now, how many points do I need to specifically say which parabola I'm working with?
5.
3.
Mhm.
3.
3 points.
3.
I need 3 points because I have A, B, and C, right?
Yeah.
I have A, B, and C. So if you give me 3 points, then I can write system of 3 equations, right? And then solve it for ABC, right? Which I'm not going to do here, but we all agree. I just want to make sure that we all agree that I need 3 points to say specifically which parabola are we talking about. Okay.
Unless one is the vertex, right? If one is the vertex, you
If this one is a vertex, you still need,
no,
well, first
one
of
more
all, you
point.
don't know.
Vertex and 1 point.
First of all, you don't know if it's a vertex, right? I'm giving you 3 points and I say, okay,
Right.
how many parabolas do you have? Can you fit? And there is only one, right? You don't know if it's a vertex. If it's a vertex, it's extra info, right? Okay, now I want you to write your own parabola. And again, because I will have to do some calculations in my mind, please make this coefficients positive and smaller than 10. Okay. So everybody has a parabola ready? Okay. And now I want you to calculate, let's say for x equal 11, how much is y? Yeah, I gave you a bigger number because that's easier for me then.
Okay,
Okay, is anybody ready?
yeah. 122?
122, that's what you got, right?
Yes, yes, please.
So let me see. I need to do some thinking. Okay. So your parabola is, your parabola is tricky, right? It is, well, did you pick a 0 for the, okay, your parabola is x squared plus 1.
Yes, correct.
So
Perfect.
you got as one of them is 0. Okay, anybody else?
408.
408. Okay, just give me a second. Okay, because I usually do it in my mind, but because we are sitting in the table, I can actually do it in here. Okay, so then I have 37. Okay, 3. Okay, so your parabola is 4x squared plus 3x plus 1.
I think 3x squared plus 4x plus 1.
3x squared plus 4x plus 1. Sorry. Yeah.
Yeah, switch the
Sorry.
question.
Yeah. Yeah. Anybody else?
193.
193. Okay. So what do we get? Okay. And I will tell you in a second how I'm doing this. Okay. So it's 7, 6. Okay. So I get 1x 6x squared plus x plus 6.
No, I have different, I don't know.
Oh, did you calculate right?
Yeah, it's 11, right?
Wait, because it's 17. So you get x squared plus 6x plus 6. Oh, I said 1. Your reminder is 6. So x squared plus 6x plus 6.
No.
Okay, so we'll check this one in a second. Anybody else, or are we going to the explanation?
Your question, A, B, and C are integers, is that right?
Yes, A, B, and C are integers.
Okay. Just wanted
And
to
I
make-
want them positive. And of course, I mean, you see what I'm doing. Let's go back to this one, right? When we do the line. So look, what would happen if I say, give me the value at x equal to 10? You're writing your line and I say, oh, evaluate it at x equal to 10. That would be much easier for me, but it would be too easy for you to figure out what I'm doing. That's why I gave you 11.
Isn't 11 obviously strategically chosen? Like you could have chosen 13, any.
I could choose anything that's bigger than my A and B.
Yeah, I mean, and then your A and B are integers. So there is very little degrees of freedom here. I mean,
Yeah, but the thing is, you see, be careful, because in here, first of all, I said A and B have to be positive. Okay, so that's a big thing, because it means I can use what we were talking about. So it means I can write the number, then what you're doing, you're giving me the number that you calculated, evaluated at 11. So if I put 11 in here, right, then I will have 8 times 11 plus b. So for a line, it's I pick 11 because it's easy to divide by, right? So if you give me a number, I divide this number by 11, and the remainder is your b, right? And then, so I don't know, maybe I will wait, stop sharing and write it in here. If I stop share, but you still can see me, right? Oops, how can I stop sharing this?
You can just annotate on it.
Yeah, but wait, no, I don't, no, this is not what I wanted. Wait, let's go back. I want to share. Okay. But wait, let's see. Yeah, I wanted to write. I wanted to write on it. Okay, but I can, what I can do this, and this, no, but if I do this, then you're going back to me. Wait, sorry about that. We go back. And what I don't want to do, oh, I want to be like in this position, yeah. Because look what happens, I can write here. So if I'm looking at this, let's say I have y equals to 3x plus 5, right? So if I put 11, then I have 33 plus 5. See, and you report to me 38. What I do, I divide by 11, and I know that the remainder is 5. Because I made sure that your number is not, the last number that you have here is not bigger than 10, right? So it has to be a remainder. And then, so I divided by 11, I got remainder 5, and then I got 3, right?
Quotient will be, yeah,
30,
coefficient.
see, if I do 38 divided by 11, right? Then you get 3, remainder 5.
Yeah.
So this number is your b, this number is your slope. Okay, now what if I'm going to the parabola? Well, then what happens? Then you see, and going back to this one, what if I ask you to put x equal to 10? Then what you actually will give me, which is very easy, then if you say, take this one and evaluate at 10, you will give me 35. So I immediately would know that the remainder is 5 because I'm dividing by 10 now, right? So remainder is 5 and your slope is 3, right? Because this is equal to 10 times 3, right, plus 5. So when I'm getting this number, I divide by 10 and remainder is your b. And how many times 10 goes into it? It's your slope. But what I want, so, you know, for a line, it's easy, but for parabola, what do you report to me? Well, whatever you have here 11 squared plus b times 11, right, plus c. So see what it is? This is the number you give me. You give me a y. So what do? I divide it by 11. When I divide it by 11, I'm getting c at once, right? I'm getting a c because this is divisible by 11 and this is divisible by 11. So c is the number. So let's say, what did we have? Let's get a number that we got before, like 408, for example. So let's do 408 so everybody can see how I did it. So I did what? 408, right? And I divided it by 11. And you know, 11 is easy enough so you can do it in your mind, right? So it's 3, right? 33. I'm getting 78. And this would be 7. So remainder 1. I don't have to finish this one. So my last number here, I already know it's 1, right? Then I'm working this one, x times what? Well, I'm taking this number now and I divide it by 11. You see, because I divided already by 11, I know the remainder, and what's left, it was already divided by 11. So if I divide it by 11, I'm getting a 3. So it's 33. Remainder is 4. So I know this number is 4. Okay, and then I should divide 3 by 11, but I know it's 3. So this was 3x squared plus 4, x plus 1. Everybody with me? So what we are doing here, we really representing this number 408 in 11 as not binary system. We representing it as 11 system. Okay, everybody understands what I'm doing? So this is how you do the trick,
Yes.
right? You just divide it, and 11 is good enough. Now, what if I say evaluated x equal to 10? Then I will get, this would be 10, this would be 10, and this would be this. So it would mean 10 squared is 100 plus b times 10 plus c. So I immediately know what are the coefficients. If you ended up with 408, I know that it's 4x squared plus 8. But it's so easy that it's, for people to guess, so you don't want to use 10. You want to use 11, but you have to make sure that all these numbers in here are smaller than 10, smaller or equal than 11, so 10 or less. Okay, so we figured it out. And now I sort of segue to what is that I do with my students. And this is more towards activities and projects, less than guessing. So algebraic geometry is connection between geometry and algebra. So for example, analytic geometry, like calculus stuff that you are teaching, this is part of algebraic geometry. So what does algebraic geometry study is algebraic varieties, which are really common zeros of equations. So you know a lot of them. I mean, this is a line, this is also a line, this is a parabola, this is also a parabola, this one is a hyperbola, this one is a circle, right? And this one is empty set, right? If you're doing in reals. So you, of course, may write the equation in such a way that you have a parameter, and in here you have family of parabolas. These are all parabolas. The only thing that changes is a. So it's different a's for this parabola, and you can study a family. We can also study a family of algebraic curves. So this is generally what your students are not doing in lower level mathematics. However, this is a very good thing for the project because this is something different and they really like it. So if I start with y squared and write a cubic equation on that side, I'm getting something called elliptic curve, which may inspire your students to do more math, because this is the hottest thing on the market nowadays. And I will explain in a second why. And you see, if I'm changing this a in here, a and b, I may get differently looking curve. Now, look, you can get, you have all sorts of graphing tools available to you right nowadays. The only thing, if you want to do this kind of activities, you have to make sure that they graph implicit equations. Okay, and they are like gizmos online, and whatever you have, Mathematica, MATLAB, and so on. They do graph implicit equations. So you're getting a lot of different curves like this. And of course, you don't have to do it on a plane. You can do stuff in 3D. So see, these are some examples of these are all polynomial equations, okay? This is not like a really big deal. You don't have unusual expressions in here, but you want to study these ones and you want to figure out what are the properties, which ones are similar and not. One of the things that you want to study is what are the symmetries of the surface. So say this one, that sort of rotates, so it has rotational symmetry in here. But you study a lot of different things, like these pointy things. These are singularities. You have singularities here. You may have a line that's on the surface. and so on. So there are a lot of things that you can study. Okay, and they are all given by equations, and it could be depending on usually you study them in R3, so they are given by one equation, but it could be that you may have more equations and cut them out from the bigger space. But that's sort of what is the basic stuff that we study. Now, the big question is, and this is something that you do in calculus with students at the end of the Calc 3, is classifying degree 2 surfaces. Okay, and anybody has an idea how many different types of surfaces do we have if it's only degree 2? This classification is done. So it's just the question is, I write an equation, quadratic equation, meaning like x squared plus y squared plus xy minus 3x plus x plus 5 equals to 0. How many different types of equations like this can I write? Well, the first thing I will give you the answer. So depending how we classify them, but there are like 17 different cases. First of all, you can have a sphere, right? And if you look at this, you see this one is done in Mathematica. It's a bit different than the other ones, and I will explain. But see, I can have a sphere, and it's a special one because it has a lot of symmetries. Then you can have spheroid, right? That it means that if I cut it this way, right, then it will have a circle. You can have ellipsoid, so it means depending if I cut this way or this way, I'm getting an ellipse. So these ones are 3 different ones, really, from the point of view of classification. But then you can have a cone, right, which is kind of popular. You can have a parabolic cylinder, so this is parabola going all the way. You can have hyperboloids and so on. So look, we have all these different types, but it can happen that maybe I'm getting 2 intersecting planes, right? It may happen that I'm getting 2 parallel planes. I may have a plane that's a double. I may get a point. For example, point is a solution to equation x squared plus y squared equals to 0, right? And there could be no solution. If I have x squared plus y squared equals to -1, then I'm getting an empty set.
Excuse me, can you define again the degree 2 surfaces in R3?
It's the degree of the polynomial.
So how can you get so if you've got only 2 variables, and let's say z is your function of x and y, correct?
Right, so you're getting, right.
How can you get a sphere if z equals to a polynomial of degree 2 in x and y?
Well, no, you have 3 variables, but degree is 2.
Okay, now
the equation of a sphere is x squared plus y squared plus z squared equals to 1.
I agree now. I know, because originally you only set the x and y.
No, sorry. If I said x, so this is x, y, and z because it's R3.
Okay, yeah, and also you also mentioned the word implicit, which closes and everything, pulls everything together. Implicit equations, okay.
Right, and this one's actually in R3, I do not have anything that requires implicit equation.
What's that again?
I mean, all the surfaces in R3 that can be described by one equation and of degree 2, if they are of degree 2. And look, and this problem was, this one's degree 2 are very well known, and this was solved like, I don't know, long time ago, 100 years ago, probably already. And the next step was, of course, to look at the cubic surfaces. Okay, so see, and this was actually, I have x, y, and z here, make w equal to 1. Okay, because these equations actually are written in so-called projective space, but for us, w could be 1. We don't need this variable here. But see, if they are of degree 3, so this equation would be 4 times x cubed plus y cubed plus z cubed plus 1 equals to x plus y plus z plus 1 cubed, right? So I'm getting something like this, and this is called Cayley cubic, and it was studied very extensively like 100 years ago. And or Clebsch, which is x cubed plus y cubed plus z cubed plus 1 equals to x plus y plus z plus 1 cubed. These are nice equations. It turned out that this classification is very complicated, really very complicated. But there were some interesting things that you could say about the surfaces, that they all have lines on them. So there are lines on them, and here you see the pictures of some of the lines. And one of the nice exercises is to ask students to find these lines for the ones that are having nicely written equations. See, these equations are sort of worked out in such a way that they work nicely. And the fact is that you can have up to 27 lines on the surface of the grid tree. So one of the ways to classify them is to say, okay, this one has 27, this one has 26, and so on, and figure out this classification. Look, it is not perfected. The classification of cubic surfaces is not perfected. And then, of course, what's the next question? How about higher degrees? See, and this is like a piece of this, but they are coming out very unusual, looking very nicely and very modern way. And this one is, as an example, is quite recently discovered in 2008. This one is of degree 12 and has 600 nodes. So it means that these points, you see these points that are that also of sort of self-intersection. It's 600, it's the biggest number known. And look, because we do have computers that can graph for us, not for such a long time, this is really a big area of research right now. Okay, not only, you know, studying the surfaces and finding surfaces with specific properties and graphing them and so on. Now, one of the things that I have done with my students, they would study a specific surface that was given to them and study all the properties. So this is one of the posters from one of the conferences, and the name is given to the surface by the student. Now look, what we're talking about so far are the surfaces that are in real space. However, as we know, we have complex numbers, right? So I said that if we're looking at x squared plus y squared plus z squared equals to -1, it's an empty set in real numbers. But in complex numbers, this one is not empty. So by the fundamental theorem of algebra, I hope everybody remembers, you can factor any polynomial into linear components. So every polynomial you write will have a solution, will have a graph. These graphs don't look differently because, for example, these are curves in complex space. So this is we see it as a sphere, but this is dimension 1 in complex space. This is also dimension 1. It's a torus. This is also dimension 1. It's like a you know, that's like a donut. This one is like a double donut. Okay, and so that's one way of looking at the solution. If you want to go complex, you can go and study this kind of curves, and it turns out these ones are called curves actually, and it turns out that the only ones that exist are the ones that are built out of donuts. So I have one donut, then I can have 2 donuts, then I have 3 donuts, 4 donuts, 5 donuts, and there are no other curves in complex space. Okay, now I don't have that much time, but you would say, oh, well, we all know what an ellipse is. I take 2 points, I call them foci, then I take a certain distance, and an ellipse is the curve that has the sum of these 2 distances to the point on the ellipse constant. So from here to here is a given number d, and from here to here would be the same d, and from here to here would be the same d, and so on. So it turns out that there is a revival of ellipses. Okay, it was for a moment, for a time being, we thought, okay, well, everybody knows what an ellipse is and so on. But now we start looking at them a bit differently, and I will tell you how. So first thing is, really, how do I write this condition, right? I write it in such a way that I want the distance from this point to that point, plus distance from this point to that point, to be given to my given constant, let's say d. So this is the Euclidean distance formula, right, for this distance. This is the Euclidean distance formula for this distance. And I want this, right, to be equal to d. And if you look at this equation, you say, wow, there is a problem. This is not what I teach my students to be an ellipse, because ellipse looks like x over a squared plus y over b squared equals to 1. So the first question is, okay, could that be put in this form? And the answer is yes. Now, if you try to do it, and I have it as an exercise here, but if you try to do it, I mean, what do? You square both sides, right? And you get rid of some of the roots. But you cannot get rid of the roots if you square it once. You have to square it twice. If you square it twice, then you're getting a polynomial, but this polynomial is of degree 4, which is not what you want here, because this one is of degree 2. And if you can manipulate your equations well, you will find out that actually it's factorable. And it's factorable in such a way that two factors are identical and give us this. Okay, and then we can put it like this. But what's new? I mean, this is nothing new so far. What's new is this. Well, because in traditional ellipse, we would say I have two foci and I want this distance to be constant, right? And actually, very special case of an ellipse is a circle where they overlap, right? So I have really one point and I'm getting a circle. So from here to here is the same like from here to here and so on. But now it turns out that in business applications, they want to have more than one foci, more than two foci. They want 3 or they want 4. And see in here, you see the examples. These are the equations, right? So they have this root stuff in them. And if I put these 3 foci in such a way that the third one is in the middle, it sort of looks like an ellipse. But if I put them not symmetrically, see, this is not an ellipse anymore. It changes. If I have 4 in here, and it doesn't look like an ellipse. If I have 4 like this, it doesn't have to look like an ellipse. What more, this condition that you have to be at certain distance from a point happens to be not enough. You may want to be certain distance from a line. So you see the blue things are foci. I want the distance, or say I have this point, I want this point to be in a given distance from this line, this line, this line, that line, and that line. I have 5 foci here. They all are lines. And I want to make sure that whatever figure I will get, the sum of all the distances to these lines is constant. It's given. So see, we call them generalized ellipses. And K means how many different foci you can have. So say 5 points, 6 points, 7 points, but you may have 5 lines, 1 line, 2 lines, 3 lines, and you may have also mixture. I can have 2 points and 1 line, or 2 points, 1 line, and 1 plane if I'm going to higher dimensions. So in higher dimensions, this is what we are getting. Your familiar cylinder is, for example, a collection of points that have the same distance from a given line. But these ones are with examples of the ellipses when you have different number of foci in space. And you see these equations are getting very, very bad, and they all have roots. So that's not really our favorite thing. That they have roots, but what happens is See, even with what you want to do, you want to get rid of the roots. So if you keep multiplying and try to obtain a polynomial, see this ellipse will get this polynomial, okay, after you multiply it out. And then when you graph it, you're going to get a very complicated figure, something like this, where your ellipse actually is included. It's this one. The ellipse is in there, right? But this equation is algebraic. We can apply algebraic geometry here. This one is not. And so there are a lot of interesting things that may happen in here. And unless you have some questions, see, these ones are examples of what happens with them when you go and change into algebraic equations. So see, this one is the ellipse itself, but these ones are a vision of actually what does it look like if you get go to algebraic equation. Okay, same in here. I have this one and it gets growing. These are visions of it. Okay, and these ones are actually projects that my student had done. So here are some results. I know that it's too quick to really go through it and my time is up, but I'm saying that there are a lot of nice graphical projects for your systems, for your students. And one last thing that I want to mention, maybe in 2 minutes, it's we all know that cryptography is important and so on. The very old way to do cryptography was to number all the alphabet. And so you're really not sending letters, you're sending numbers. The best crypto system that there is the RSA, which is military quality. To break it, it's impossible. Okay, nobody broke it. Now, what does it require? It requires special prime numbers very large. And the big thing is that you decrypt it in such a way. So this is your message, say I'm sending number 7, but instead of 7, I'm sending out 7 in power e. I send it out, and then to decrypt it, I have the secret code that gives me the way to decrypt it, which I take the number I got, I even raised it to higher power, and I'm calculating modulo specifically chosen number n. This is how you decrypt it. This is really impossible. I mean, it takes forever for computers to break these codes. So elliptic curves that we looked at in a second ago are much faster to calculate. This is what internet is using. So what do? You need an elliptic curve. So you need the curve that looks like y squared equals to x cubed plus something. You need some points on the curve which have certain properties. You need the number that you give out so everybody can encode, and you have your secret number that you can decode, something like this D. D is secret. And this one is really quickly computable, but it's really hard to break. Okay, the DLP means discrete logarithm problem. It's almost impossible to do if your curve is well chosen and if your numbers are well chosen. So again, this is an elliptic curve. So it's y squared plus x cubed plus some ax plus b. You can always write it like this. So you need to pick up this a and b, so they are sort of good. So the first thing you want to make sure that your curve is good. And what you do, remember, it's a cubic, right? If I have a cubic on a plane and I take a line that crosses it, it has to cross it at 3 points. So if I want to send this number p as a message, so let's say p is my number for coding. I want to set the message q. If I send q, everybody can read it. So instead of saying p sending q, I'm sending r. So I'm sending the point that this one and this one, that they are on the same line. I'm sending q, but instead of sending q, I'm sending ur. And then instead of sending ur, I'm sending ur star, which is the reflection. Okay, so now it's really hard to figure out what was sent, right? And it's really quick to decode if you know what you're doing. You know, in a minute, we're not doing it this way, really. and it goes back to all the other stuff that I was talking about, because what is the problem? I mean, this is a curve, this is smooth curve, it has millions of trillions of points, and we want to be accurate and so on. So what do we do instead? We look at this curve over discrete fields. So I'm calculating modulo. Okay, I'm calculating modulo. So I'm looking for all the solutions to this curve, modulo, say in this example, 13. So what do I get? I'm getting a bunch of points. Okay, and these points are on the plane. The initial, the black thing is all the numbers that are smaller than 13 in here. So these are all the solutions, but actually, remember, this is modulo 13. So these ones are the same ones, modulo 13, and the next ones, and I can go to the top and so on. So if I want to send a message, say, I want to send this number and my starting number is this, I'm going up, it has to intersect, same thing like before, at the third point, this, and I reflect this point here, and this is what I send out. Okay, so this is what I send out, and this is why is it very quick if you're calculating it on the internet, the way the stuff on the internet is done. Now, of course, you don't want to use number 13 as your fee, as your modulo, because it's too easy. I mean, it's too easy because I can like get all the things written down. These are how many points I have on this curve if I use 13. So it's, I mean, it's a lot of points, but not enough, really. So you want a good crypto system. So you want the large prime number P, and you want to pick a good point, starting point P, and you're using to do the cryptography only the points that are multiples of this P. So I want to add P plus P plus P plus P plus P, and I'm only using these ones. Okay, and these are the conditions that you need to satisfy to make sure that the curve that you picked is good. And look what it says, that you want the curve that has at least 2 in power 160 points. You see what I'm saying? It is not a small curve. It has a lot of points. Mm-hmm. Now, what is your P? Well, your P, you can take your prime, or you can take your prime in some power. It works also good. And you want to make sure that this is bigger than 2 in power 1024. Okay, so you see what I'm saying? These are the numbers that we are talking about. And this is an example. So one of my students was searching for a new curve. That's an example that she came up with. So this is a very large prime number, right, that she used. And this was the number of points that you had on this curve. And this was the point. So the point had this kind of coefficients in this, you know, this is Z huge. So this one, this coordinate and this coordinate is smaller. Point has 2 coordinates, right? Mm-hmm. Now she did this one and then she improved. Okay, so this is a better solution. Why is it better? Mostly because you see this number is a bit smaller, so it's easier to calculate. Now look, elliptic curves, if well chosen, so far it's very hard to break them. The bad ones, that's why you have conditions in here. How this curve should look like. See, I have a lot of choices there, so I can pick whatever I like, and I have to pick up this field as well. And once I have the field, I have a curve, so I have a lot of points and so on, and I can get the thing. So this, I'm at the end of this talk. I just want to tell you that we do have at the University Channel Islands, we have associated group that deals with gaming and other funny materials. So if you go to Amazon, you may look for a set of poems about algebra. Okay, and it's very nicely illustrated. Okay, there is also the one about numbers. So this is really like foundational, starts with easy, but goes to infinity and so on. And these are all poems. And we also have a logic game, which actually I was told that they're renovating it, so it doesn't work at the moment. But so the group is Educational Games Research Institute, EGRIS, egris.org. And unless there are any questions, okay, I'm done.
Dr. Grzegorczyk, yeah, there was one question in the chat box asking about your text, Mathematics and Fine Arts. It's no longer in print, so they were
It's no
asking, is there a
longer in
way to
print.
get a digital copy of it? Is there a possibility of getting a digital copy?
You try Amazon. Sometimes people sell it. You know, I know that at the university we just made copies of it for the students.
Got it. Okay.
Okay, it's Mathematics and Fine Arts, and this one is dealing mostly with patterns and groups acting on them.